say, over the past 10 years on improving, measurement capability at the nanoscale, specifically for certain type of materials, would be fair to say, focused around electrical, electronic, and magnetic characterization. My talk is really going to, focus more on data and results using, some of these advanced AFM measurement techniques, and less on, our own product itself. Of course, most of the results I discuss and present to you are going to be, from our platform. But this is really a sort of the idea is to give everybody an overview of what's possible these days in terms of measuring essentially electrical, electromagnetic, and electronic properties of materials at the nanoscale. As the technology improves, in designing, these surfaces and devices from the bottom up. It's only possible because many of the characterization techniques, primarily probe microscopy based, are able to give us, reliable data at such low length scales, at these resolutions down to, even a few nanometers these days of functional response of materials, which then obviously allows technologists to go ahead and design and pattern and even coat many of their surfaces to gain these bottom-up functionalities and properties. So just to sort of, spend a couple of minutes or even 30 seconds really on the design of our platform. It's quite a compact platform, and, as most of you probably realize, the essence of measuring something so small is in being able to decouple the signal from the actual, instrument measurement itself. And hence, it's quite important in atomic force microscopy to have, a very compact footprint, that allows us to make noise-free measurements and keep the tip and the scan environment sort of, as compact as possible. And that is what we have translated into the design of the nano observer. So if you follow the laser pointer, you'll see that, we've got a pretty compact design, and that's sort of environmentally isolated as well, with only the tip and the sample really, in the sort of the active region, as we could call it, allowing us to sort of, minimize background noise, improve signal to noise ratios, and make focused, nanometer resolution measurements, for advanced properties, not just, topography, imaging, and the regular applications of atomic force microscopy. So, again, just to give you a quick overview of, where the company has its history in, we have been Europe and many other countries around the world, the distributors of, some of the early pioneers of atomic force microscope systems like Digital Instruments, moving on to Agilent molecular imaging and Bruker at a later date. We at around, in the early 2005, we sort of, got together and decided to sort of, bring and translate, all of our learning in the field of AFM into developing a product of our own. And, the result of that is the Nano Observer. So, we like to see this as, in a sense, a boutique AFM that really brings in the best of the design that's available in the industry to be able to sort of, make specific measurements with the highest resolutions possible. Our website is csinstruments.eu, and there's a wealth of information on it. And, hopefully following on from the discussions today, we'll have many queries, and we can always keep following up on that. So just to give you a quick sort of overview of, some of the measurement techniques that we excel in. And as the slide will readily give you a flavor, is our primary focus has remained to obtain the highest possible resolution that AFM platforms can provide in making direct electronic and magnetic measurements, with techniques such as Kelvin probe microscopy, something that's proprietary to us that's called the resiscope. Can everybody hear me, by the way? Dr. Poddar, is everything good?
Perfect. Very nice.
Okay. Okay, thank you. Yeah. So that's the real idea of our platform, and yeah, I will be talking you through these modes, because some of these modes try and understand, the measurement techniques that lie behind some of these names, and these sort of samples that we can measure, and the resolutions we can expect, and what's in the future really of making more and more high resolution measurements that pushes the boundaries of some of these nanostructures. So I'll be touching upon each of these different measurement techniques. I would like to sort of obviously underline the fact that, the platform itself, of course, covers all conventional sort of measurements that have been made over the past 2 decades using the atomic force microscopy platform. But obviously, we like to highlight, some of the measurements where we focus on, namely, nanoscale electronic and magnetic measurements. So obviously, this essentially directly puts us, into certain applications, spanning from, fuel cell batteries to PV solar cells to, memory devices and electronics, really. So I'm going to begin with what is now quite a reasonably well-established technique in the field of atomic force microscopy, which is to measure the surface potential of either pattern surfaces, coatings, or a nascent substrate itself, and to really map its surface field potential. We call this mode HD-KFM, borrowing the HD from the term high fidelity. So, that's trying to underline that, we probably offer, the industry highest resolution in making contact potential and surface potential measurements, which are obviously related to the work function of all materials. And it is obviously a fundamental property that you want to interrogate and characterize, for your applications. Just to give you a brief history, and I guess, I noticed that, there was a presentation of KELVIN Probe Microscopy as well previously, so I'm not going to spend a lot of time on it. But I think what I would like to highlight is, the fundamental, and this is really to understand how technology progresses.
Can I request you something?
Yes.
I would like you to go slow and
okay.
Please spend as much time as you want.
Oh, okay, fine.
But the message should be clear and to the students, because a lot of students are there.
Sure. So would you like the students to...
Don't rush for the time, okay? Yeah.
Okay, fine. So would you like the students to sort of, interact live, or should they save the questions for the end?
As you wish.
I'm open to both. So, as long as somebody has a question, please feel free to sort of, raise your hand, and we can have a discussion, no problem.
So as if just consider you are a professor, you are teaching, not just a company person. Okay.
Sure. No, sure. Yeah. So so maybe it then makes sense to spend some more time especially with students on this. I think this is fundamental to understanding how technology develops really, and how we have gotten to this point where we are really in a position where we can design surfaces and materials and devices at the scale that we can do today. So as you probably know, KELVIN probe microscopy is really a very old technique. It's 100-year-old maybe in terms of the proof of the concept. Let's say the original clever setup that was designed by Lord Kelvin. What he essentially established is that the whole concept of contact potential difference, which is directly related to the work function of materials, of course. And the setup he used to do this was simply, what is now ubiquitous in our labs is a simple plain capacitor type of setup. And he was able to measure, the charge differences between, what he used as zinc and copper, and hence established that, there is actually the term called contact potential difference. And it is really an intrinsic property of the material that's related to the work function. So the investigation that he did was obviously, not at the nanoscale, because, instrumentations that could probe, the surfaces at this length scale didn't exist at the time. So his setup, I believe, was, down to maybe using capacitor plates of several centimeters. Some of these, this was then improved, as you will see on the slide, maybe about 2-3 decades down the line. And this is where, we begin to move into, what's really involved in development of instrumentations, because when you're trying to find out the property of materials, surfaces, intrinsic to it is the fact that, you have an instrument, and the instrument has its own errors, it has its own way of measurements. So it is coupled, into the measurement itself. So to be able to measure your surfaces, you need to understand, what instrument you're using to measure it, really, and this, I guess, goes down, at the quantum level to the entire question of uncertainty, so you cannot decouple, your instrument from the measurement that it's making, and that's the basic idea. And hence, it obviously follows that, the instrument you design has to have, as good a performance in terms of, isolating the intrinsic signal from the sample itself, rather than, it being convoluted by the measurement of the instrument itself, if that makes sense. So, and really, this is a nice illustration of how technology progresses, and, we come up with more and more setups and instrumentations that allow us to make more sophisticated measurements, on fundamental physical principles, that have really been demonstrated for, even hundreds of years now, such as Kelvin probe microscopy. And Zinsman, for instance, in the 30s, actually sort of modified the setup, where, he moved the idea of having a sort of a surface to surface, like a capacitor type of a model, to, changing one of the surfaces to a tip. So, once you have a tip, obviously, you can imagine, you're able to probe the counter surface, which is a bigger area, really, a lot better, because, you're decoupling the effect of a second surface, really. So the tip is essentially a point contact that allows us to interrogate the counter surface free of, two surfaces, really. So you have, really a point detector, let's say, or a tip, for instance. And that's what Zinsman sort of attempted to do. And obviously, this resulted in a much better resolution, because now you're not, essentially, you're not probing, a brick with another brick, but you're probing a brick with a pin, and obviously the pin has a much smaller surface area. And hence it allows you to probe, similar surfaces of similar size in the brick itself, So you're looking at, tiny points on a surface a lot better than, trying to probe it with another surface of the same size. And that's the real idea that, Zinsman translated. And he was able to make, micron range resolution measurements with Kelvin probe microscopy. So moving on to how we do this today in atomic force microscopy, as most of you, or I presume all of you, are aware that atomic force microscopy, the physical principles of it, is essentially quite simple, and it's translating down the same concept that's been used in the 1930s. Let's say, is that you have a point probe, and once you have a point probe, if you get it right, ideally, you're able to interrogate, your sample at resolutions that are comparable to the size of the point itself, So now, obviously, in reality, you can't really come down to a point, but, modern day cantilevers of atomic force microscopes allow us to have contact areas of the order of a few nanometers, and these are the direct sort of, interaction, the interaction scales between the tip and the sample. And essentially the movement of the tip, in response to how it interacts with the surface, so when you're measuring topography, it is simply scanning along the surface, and the physical topography of the surface, is then captured, in various electronic signals processed, and you develop your image, So it's just like walking over a surface. You get a feel of, what you're walking over. In the same way, the cantilever essentially, scans and walks over a surface and produces an image of it. This is obviously the most traditional use of a scanning probe technique that, we're all accustomed to, I guess, and has been in play, for the last 25 years. What has gotten more sophisticated is our ability to make other different type of measurements, understanding not just the surface or the topography of the surface, being able to interrogate some of the functional properties of these surfaces, some of the intrinsic properties at very fine resolutions, at resolutions of a few nanometers or below, really. And and this is, some of these techniques obviously are, dependent upon. So essentially what the cantilever is doing is feeling the force field, that it's scanning across, and force fields can be generated, as you all know, from short order forces, which are related to sort of, van der Waals forces, really. And you have, relatively long order forces such as electromagnetic forces. So hence, if you want to make reliable measurements, of functional properties of these surfaces, you've really got to be able to decouple both these interactions. You've got to decouple these short range interactions, that will really give you data related to the topography of the surface. And, you need to be able to make some long range measurements, like magnetic properties of the surface, ferroelectric properties even, and fundamental, electronic properties like work function and dopant densities and that sort of thing. So just to illustrate to you, how this is actually done on the instrumentation side, because, appreciating, how a measurement is made always allows us to understand, what we are measuring, really. And that is, I think, fundamental to, all of you as, you go on and research a variety of surface of, a variety of materials, a variety of different applications, is, what are you measuring with, because what you're measuring with will ultimately decide especially at the nanoscale, what you're measuring. So that's very important to understand is, it's not, and no instrumentation is really absolute, it's measuring signals, and hence understanding how these signals are measured allows you to interpret your data a lot better as to, what the measurements really mean. In the case of, how we get around this whole issue of, measuring forces or measuring interactions or properties of the surfaces at two different length scales, that is short range forces and long range forces. The way that is done, in all modern atomic force microscopes is by using two lock-in amplifiers, and one taps in, for example, for the short range topography related forces, and the other, simultaneously tuned on a higher harmonic of the cantilever's oscillation, is able to precisely capture, things like the surface potential of the surface. So if anybody has any questions at this point, I can either take them now or, we can leave them for at the end of the discussion, really. Yeah, Neelu? Hello? I have a raised hand from Neelu, so I'm just going to wait for a second for his or her question.
No, he has no question. Please go ahead.
Fine. All right. Okay, fine.
Question.
So yeah, and let's move on to what do we really see? And this is a snapshot, I guess. I'm guessing this is about maybe 5 microns in size. The image here. And we're trying to illustrate what I just discussed. You mechanically oscillate the cantilever at multiple frequencies. You decouple, the response to each of these frequencies. One of the frequencies, typically, the lower eigenmode is used to infer the topography of the surface, which is really at the top here. And, you can see this is some sort of a device, that has been, I guess, doped along these topographies. And if you look at the bottom image, you can see that this is the actual surface potential density difference between region 1 of the surface and region 2 of the surface. The color coding really represents a difference in the contact potential or the work function of the material. So in this nomenclature, dark blue represents something that is at a higher work function or at a higher surface potential, where green and other grades represent surface areas that are typically at the lower resolution. You can see these spots around here, and obviously, these are just impurities or not really impurities, sorry, like dust and other sort of artifacts on the surface. And obviously, these have their own intrinsic potential as well as organic matter mostly. And you can see those blips come up on the screen as well. In fact, you can see in the topography, we cannot really capture some of the dirt maybe, but the surface potential signal is so clean that we can actually identify some of the dirts on this wafer that don't appear on the topography scan. So that's really nice to see, because that tells us that we are actually able to make electronic measurements on surfaces sometimes at a much better resolution than just measuring intrinsic topography of the surface. And yeah, I guess I should have brought that up before. And that's just a 3D rendering of what the surface is like. And this is just a quick recap, I guess, of the physics. So this is essentially translating the same the measurement setup that was used hundreds of years ago, really 100 years ago, sorry, by Lord Kelvin, which is a parallel capacitor measurement. So the challenge in instrumentation is to be able to translate this sort of an experimental setup, a classical setup that works at let's say a macro length scale, and to translate that same measurement principle and to be able to make measurements with reliability down at the nanoscale, where you're measuring currents, and other electronic signals that are decades smaller than what you would get from macroscopic scale experiment, for example. And that is really, I would say, it's a lot of the art and the science behind design of instrumentation, is to be able to make devices that are able to make some of these miniature scale measurements. But the physics remains unchanged, of course. The fundamental physics remains unchanged. And that is what I demonstrate in the next slide here, is that, we are using the same concept now, is bringing essentially a point, for all modeling and empirical purposes, a point surface, that is the tip of a cantilever in contact against a sample, that is typically, a few length scales, greater than a point contact. So you're really modeling this as a point against a flat surface. And by vibrating the tip, we are able to sort of, use mathematics to filter out, the signal of the surface that is related to its intrinsic charge characteristics, rather than the height of the surface or the topography of the surface. And really what we need to be able to do this is, some very sophisticated electronics, which really I think is slightly beyond the scope of this presentation, perhaps, but suffice to appreciate the fact that the better the electronics you have, the cleaner will be your measurement, and the better the electronics you have, the more precise measurements will you be able to make. And this is an illustration of something I guess I just talked through as well. So, important to remember when you're looking at, deciding a tool to characterize your surface, to understand that, scanning probe microscopy, which is probably, the primary beast most people use these days to, interrogate the nanoscale, is that, there are various, you have to know what you want, what you want to measure and what you can measure. And really what you can measure are sort of, forces and interactions across the length scales, from short range forces to, long range forces. And that's really the, and that these two forces sort of combine to give you the net interaction that you're measuring. So if you want to measure a short range force, like topography or something, you decouple it and measure the topography. If you want to sort of focus on measuring the magnetic response of the surface or the electronic response of the surface, you're still measuring one force, but you've got to be able to decouple it. In this case, we term it as the surface force and the electrical force. And obviously, the quality of the instrumentation will determine, how good a resolution you get in decoupling the functional measurements that you're trying to make from the intrinsic measurement, that is, the topography of the surface. And that's what we're trying to highlight here. Obviously, this problem is compounded with the fact that there's an intrinsic difference in the intensity of these forces. Long-range forces, as we know, by the very virtue of being long range, they're much weaker. So be able to capture their signals requires some clever instrumentation that we adopt in scanning probe microscopes these days. Traditionally, the way this has been done is you essentially first measure the topography of the surface. That is, you make the surface measurement, and then you would go on and actually lift the cantilever up a bit and make the second measurement. That is the electrical measurement. But obviously, to be able to get measurements on a surface with a cantilever, you want your cantilever to hover around as close to the interaction area as possible, and to be able to do that, in the last 10 years, the concept of using, multiple frequencies to be able to make simultaneous multiple measurements was introduced. And what we do now is we actually don't lift the cantilever anymore, but we simultaneously measure the topography of the surface and its work function or electrical properties by oscillating the cantilever at a different eigenmode in a higher harmonic, and essentially using two lock-in amplifiers at the same time. One locks into the topography signal, and the other locks into the functional signal. That is the electronic measurement. And that's what I'm illustrating here, is that the surface measurements that's related to the topography is measured in this part of the loop, whereas measuring the electrical response is actually measured in this part of the loop. And each is got its own lock-in amplifier to be able to bring out seamless actual data from filtered out from the instrumentation itself. And obviously, as it follows, one is really, from the surface, what you get is essentially a mechanical vibration. That is, the surface is physically sort of resulting in the deflection, or a mechanical deflection of the cantilever. Whereas one can argue that, when you're making electrical measurements, the deflection of the cantilever is recording is because of some sort of a potential difference. And hence, what you're seeing is an electrical vibration. So, that's nicely decoupled for us, is that, you can measure the mechanical vibration as well as the electrical vibration of the cantilever. Obviously, to measure the electrical vibration of the cantilever, you will need to have the cantilever coated with some sort of electronic coating. And typically, there are many material candidates for this. You could have your tip designed wholly out of diamond, and then you'll probably get the best signals. But you can might as well have, various things like platinum coatings and things like that. There are a number of options available in the industry to for your choice of electrically activated cantilevers, so as to speak. So here's some typical data now, where we are actually able to translate, the measurements that make into equivalent work functions. So as you will see, in this semiconductor surface itself, it is patterned in such a way so that you get preferential work functions at the different the designed surface. So you can see that you get various work functions all the way from minus 0.2 to about plus 0.6. And how do we really know about these work functions? These are typically dependent upon lookup tables. And as you can imagine, when you're translating, a lot of these lookup tables, you got to remember that, most of these values for work function that we have, that we're using here, for example, some of the highlighted ones like gold, palladium, or platinum, these are typically conductive materials that are used as the cantilever tip. So, when you're actually trying to measure you're trying to get a numeric value on the work function, you've obviously got to, of your material on the surface, you've got to know the work function of the cantilever itself, And what you've got to remember when you look at the cantilever work function is that most of the values that are available are really for bulk materials, So there's going to be sort of, obviously some difference in the bulk work function of, bulk platinum compared to, what's coated for a few nanometers on the cantilever tip itself. So I guess it's fair to say that when you're measuring work function of materials, you're often sort of really talking relative rather than in the absolute terms. Although the absolute measurements are pretty close to what you would expect, but it's important to remember a lot of these lookup tables are translated from the bulk properties of the materials and not really sort of like platinum on the very fine tip of material that's really sort of a few nanometers thick. And this is a nice illustration of how we calibrate some of these measurements. So if you sort of set the work function of gold, for example, at 0, you're then able to then make the relative measurements on something like silicon and aluminium, in this measurement here. So this is more about sort of calibrating the setup, which is really measuring a relative interaction between two surfaces to get an absolute number value of the work function of the surface. So you need to calibrate it against a known material that has a known work function and bring that to 0. And I'm now going to move into sort of getting some looking at some actual surfaces. And I don't know if you're able to see the video, because if you are able to follow the video, you will see that there are changes taking place on the surface. And this is, I believe, this is a freshly cleaved. Yeah, this is just a graphite surface actually. And what you would observe here is that we are actually changing the humidity, just the humidity of the interface. So we are just changing the humidity at which this graphite layer is subjected to. And as the humidity changes, you can see that there are various positions in this surface, and I think it's about a couple of microns wide. And you can see that the surface potential of of the graphite itself is changing. And this is over a period of 30 minutes. So this really illustrates how fine these measurements can get. Is that just the change in work function of graphite, because of the change in the relative humidity of the environment, is captured in the change in the work function of the graphite surface itself. So these are the sort of measurements that we can now make. And you can obviously translate this now into sort of, some of your own surfaces where, you will be able to make such high resolution measurements, in your case, not just controlled by humidity, of course, but controlled by how you have designed your surfaces, So if you have, a surface that's designed, let's say at a length scale of about like 20, 30 nanometers, you should be able to capture these changes, from one point to the next, given that they have different properties on the surface. So, Dr. Poddar, is everything clear for now, or am I doing okay? Or
you're doing excellent.
Okay,
excellent,
thank you very much.
Very good.
Thank you very much, because I don't give a lot of lectures these days, so I'm just not sure if I'm able
your
to translate.
experience is showing up actually today.
Thank you very much. Thank you. Okay. So I guess this is becoming a slightly repetitive slide, but I think it is, and again, we can focus on this graph here, and it really tells us that when you're making a measurement, you really got to know how you're measuring it, and if you look here, for example, around this graph here, it'll become very clear to you that it's quite easy, relatively speaking, to measure the topography of a surface with an atomic force microscope, because you have a nice signal coming up, but when you're trying to make electrical measurements or magnetic measurements or other advanced functional measurements of your surface, because you're not just sort of physically designing your surface and patterning it and then finding out okay, have I got the right patterns on it, but you're patterning for a cause, right? You're patterning to impart some functionality on that surface. And hence, it only makes sense for you to then move to the next step and try to use the same tool to be able to interrogate the functionality that you just tried to impart, by physically designing the surface. But measuring that functionality often becomes a bigger challenge, as you can see here, because what you're trying to measure is going to give you a far weaker signal, and hence your instrument, in a sense, has to work many folds more harder to be able to pick up that tiny signal, and that's what sort of, let's say, distinguishes one system from the other, or, advances in instrumentation itself, and that's really the idea that I want to, leave the students with, is that it's important to understand that, it's not just, designing your sample and sort of, imparting some functionality, but when you really come down to the nanoscale, you've got to remember that these instrumentations, are essentially making a measurement, and you've got to understand, how the measurements are being made to be understand, how reliable are these measurements, and, exactly at what length scale are you measuring, and, what is the data that you get, So, the overall ambition, of course, from the instrumentation side is to be able to offer the highest resolution possible, because, these days we know that, designs of surfaces, of some of the memory devices, for example, solid state memories, these are really, at the order of a few nanometers and even lower, So if I've designed a surface, that has features, functional features that are of the order of a few nanometers, obviously I need to be able to have instrumentation that is able to capture this lateral resolution, that is also able to measure the property of this feature in a few nanometers, and this is, I guess, a nice illustration of how the instrumentation, in scanning probe microscopy, when it comes to measuring, electrical properties of the surfaces, have evolved over, I would say, over a period of 10 years, really, This is the old technique, where we would do a dual pass. So as you can see, and we are only looking at the electrical signal here, and this is a graphene surface on silicon oxide, a graphene layer, sorry, on silicon oxide. And as you can see, you have a certain resolution for the graphene, and this is really the old technique, where to measure the electrical signal. Unfortunately, you have to lift your tip a bit, and it's that lifting of the tip that results in the, the haziness or the lack of resolution. Which at the time, of course, was great resolution, but things have improved since then, and we are able to come from, where we were in the 2010, for example, to making these sort of measurements to coming down to here, where you can clearly see, the difference in clarity here. Sorry.
That's what I've been using. Yeah. That's what actually, it's very interesting for me to also update that I've been using this top technique, which is very standard, dual pass. But what you are telling is something very interesting and new. So please go ahead.
Sure. Yeah. So, as you can see that, now you're able to see, and as many of you probably know, graphene is then going to be further functionalized, right? And as you can see, in the picture at the bottom here today, you are actually able to look inside the flake itself, and get some of these resolutions down here. And I will come to some numbers later, on what sort of lateral resolution numbers we have. But the lateral resolution, that is the spatial resolution really of these features, is quite important. So you can see that, within like a flake on the silicon oxide itself, we're now able to go inside and really look at, so if you're going to, deposit some, for sensor applications, for example, you're going to functionalize the graphene layer itself. You can now today expect actually to be able to get characterization, within that small flake itself, and hence understand, whether the functionality that you're imparting has actually translated or not in a certain sense, and that's really what I want to highlight. So if you look at the top surface here, the top image 10 years back, you didn't have, you were really shooting in the dark, and hoping that you're able to measure some of these features. But today, thankfully, we're able to do that, and I think, how we're able to do this is really, sort of, slightly beyond the scope of this presentation, perhaps, but, suffice to say that, it's thanks to, advances in digital electronics, really. And obviously, if we draw a profile through any of these images, we will be able to capture, the actual resolution by which we are able to see some of these potential differences. Now, this is just another image, that I'll use to illustrate, the point I'm making. And this is a nice one, actually, because this is what I was just saying. So here, what you have is, a self-assembled alkane molecule that has been deposited on the HOPG, And now if you look at the resolution that you get with the Kelvin probe microscopy, you can see that you're actually able to image, the molecular nature of the alkane deposition itself, So you're really able to, and this is not a topography image, this is the electrical image, So you're really able to capture this, down to a resolution of, and what's the length scale here? Yeah. So each of these alkane molecules are about 8 nanometers, So you can directly see that, we are now able to go down to, understanding, responses, the electrical response of a material down to about 5 nanometers, and that's really important because, for instance, just to give an idea, when you look at some of your USB thumb drives and, solid state memories.
Kunal, I have a request. Whenever you show these nice results, can you also mention to the students the conditions, like whether these are UHP measurement or ambient conditions, and what was the state? So those are very important, actually. So was it taken in ambient or it was in UHP chamber?
I cannot say for 100% because I didn't make the measurement, to be honest. I believe these are ambient measurements, but it's quite possible, that these experiments were conducted, when the sample tip environment was purged with argon, or a similar inert gas. So this is a very important point, of course, is
it
that
from your users or users data or
this is user data, I think. Yes,
public
this is
data?
user
Okay.
data. Yeah,
Maybe
this is from,
maybe later on you can send me the
I can send you these
references.
files, sure. I think this is
I will
from,
study. Yeah.
yeah, sure. This is from Saclay, in just outside CNRS Saclay, I
Okay.
think,
Okay. Yeah. So very
So
impressive results anyway. Go ahead.
yeah, very nice. Yeah. So that's an important point. The point that I've missed out so far, perhaps maybe, is that when I keep talking about the dependence of atomic force resolution, atomic force microscopy resolution, on the tip and the sample interface. What we often ignore is the fact that the tip sample interface is not inert, right? There's your atomic, the beauty and the versatility of the atomic force microscope. Of course, it allows us to make some of these very fine scale measurements in just open ambient conditions, compared to other microscopy techniques available. So, however, we can't forget the fact that the tip and the sample's interaction is going to be affected by molecular humidity, for example, and other contaminations on these surfaces. So, and hence it is quite important often when you're making electronic measurements to often be able to purge a gas, so that gas actually makes this tiny contact environment that I have between a nanometer scale tip and my surface, even that area as reasonably clean as possible, in an ambient condition, not in a vacuum condition, of course. And this is typically done by purging a gas, and maybe I should come back to, what the microscope looks like. So it's going to make it clear to you. Sorry about this. Yeah, so this is the environment that you want to focus on. So in our case, for example, here's the tip and here's the sample. And that is why we've cleverly, in a certain sense, designed it so that it is actually housed in almost a semi-closed enclosure itself. So what I need to worry about to make a clean measurement is that the cleanliness between the tip and the sample region. So often the way we control this, especially for electronic and magnetic measurements, is to normally we have another hood that closes this space out, and then this environment becomes hermetically sealed. And then we slowly purge an inert gas, so that the sample and tip interaction area becomes as inert as possible, And that is what, to a seasoned user like Dr. Poddar is going to jump up immediately, is, you need a clean environment to be able to make some of the clean measurements. So yes, Dr. Poddar, as I said, it is quite possible that this was an ambient measurement. But of course, if you have the ability, you try and move to as inert atmosphere as possible in your lab, and even purge with gases, so that you have a clean measurement environment. And really, this also brings us to something that's called repeatability, because in an ambient environment, you might, when you look at this image, people often tend to, miss the fact that, this image probably was captured after 5 or 10 attempts, or we will never know, sometimes people disclose it, often, it's not really beyond the purview of the publication, as to how much effort was spent into making this image. But, this is something you've got to remember, that, to be able to, the more control you have over your experiment, the more repeatable it's going to be, obviously, And the point being that, maybe one day, in a few days or in a week or in a particular location, you might be able to get such tremendous resolution in an ambient open environment. But, it's always a better bet to control this environment as much as possible. And hence, if you use inert gases in your cantilever sample interaction area, you can say that, you will have a much greater probability of getting these nice fine measurements and resolutions that you desire than you would get in a regular ambient environment, So, and hence, it follows that, a reasonably well-designed AFM should allow me to seamlessly move from just an ambient experiment to a purged gas inert experiment, so that I can, get closer to everyday repeatability.
There is a question for you, Kunal.
Please.
One student has asked, what represents the dot in the sample, both left and right?
Yeah, so the dots are actually these 8 nanometer molecules, So this is the molecular resolution of a long alkene chain, So I and again, I'm a bit out of touch with some of this research, to be honest. But the alkane chain, as you know that graphene flakes will be functionalized with various different kind of functional materials, right? Typically monolayers, for biosensing I guess some sort of a sensing application. And maybe Professor Poddar can sort of correct me on some of this.
Self-assembly of KELVIN
Right,
molecule.
right.
I think there is one student here from Central University, Hyderabad,
Right.
Sarvani. Actually, she was also interested in that. So
Yeah.
many organic chemists are interested, even at NCL. Many people
Yes.
approach me to get the same image. So
I can
molecular
imagine.
self-assembly. So this is quite nice, actually.
Yeah. So I think the inset, the inset, I guess how much is this? Yeah, so it's about a 50, 16, 100 nanometer, let's say, image. But yeah, so each dot, represents, the 8 nanometer, molecule of this alkane, that's it was prepared as some
So
sort
his
of a
question
mold.
is probably, sorry to trouble you. So
No, please go ahead.
his question is on this elliptical dot, blue one, and
Okay. Yeah, that's probably a dirt or a dust,
artifact.
that's that's an artifact, that's probably a dust particle or something that's sitting on the surface. And, we are able to pick up, obviously, its potential difference. In this case, it appears to be at a much higher potential than the rest of the surface. So it's a dust particle on the surface for sure. Yeah. And I think I've already spoken quite a bit about this.
Yeah, it may not be dirt particle because it looks too small for that size. Usually, the dust particles are several microns, so it is probably some substrate.
It could even be. In fact, it could even be the clump of the molecule itself, I guess. Also.
Oh yes, it can be just some kind of aggregation of molecule.
Yes, yeah. It's an artifact for sure. It's not coming from. Yeah, it's not a signal that we are interested in. Let's say. So yeah, I think I'm just going to move through some of these images now. Maybe the idea of these are really to give you an idea of the breadth of materials that we have already studied and interrogated. And maybe you can get some ideas on what you can do with your own materials. So I'm just going to run through some of these images. But this is another image again of another functionalized graphene surface, and you can see some of the nice resolution that one can begin to observe. So for people doing sort of graphene and functionalized graphene research, we have quite a lot to offer now, really, in terms of the lateral resolution of these structures. I'm going to move on to another mode of measurement, which we have also sort of spent a lot of time, and we like to think perfected, superior to what's available in the rest of the industry perhaps, and that is magnetic force microscopy. So this is looking at the magnetic response of materials. And a lot of this work, incidentally, I'm happy to share, is being done by Professor Shubhankar Vedanta at NICER Bhubaneswar, who's sort of, pioneered some of these measurements, at least really, at an international level, but definitely a lot of work, in NICER Bhubaneswar and in India in looking at magnetic response of surfaces. So, the scope of making magnetic force microscopy measurements, again, it's relatively simplistic in the sense that you're trying to interrogate the magnetic domains in your surface, and if you look at these may not always, because for example, the classic example being like a magnetic tape, for example, or a cassette tape or something like that. Its surface is very smooth, so obviously the magnetic domains are not going to appear up in the topography of the material. It'll have a certain potential difference also, obviously, compared to that'll reasonably follow the topography, if you have cracks and other things on the tape surface. But where really things become interesting is when you're able to look at the domains that are actually recording and storing the data. And in this case, this is actually some sort of a alloy surface on which we're doing it. So I apologize, but it obviously has a magnetic response. And it's the phase image where you begin to see some of these magnetic domain responses. If you look at this image on the right, And I guess what we're trying to highlight here is that we can simultaneously now make all three of these measurements. So you can look at topography, the surface potential of the surface, and interrogate its magnetic response. Really, in the matter of doing the same scan in atomic force microscopy. Typically, some years back you would be looking at doing 3, 4, 5 different experiments in time to be able to get some of these data. But now we're able to leverage the sort of electronics we have today in the digital world to be able to make a lot of these measurements simultaneously. And that's what I'm trying to highlight here. I think we have some more. I have some more slides on magnetic force microscopy, which shows various different type of surfaces and designed surfaces for data storage that we can look at, and the data we can get with what resolution. And I'm going to come to that later. But in the sequence of the slides I have here, I'm going to move on to another advanced measurement technique. Really, the name itself is called resiscope, and this is a proprietary name that's to CSI. But there are various ways of making these measurements. We obviously feel that ours is relatively sophisticated, in terms of how easy it is to make these measurements. But it is not to say that it is not possible to make such measurements with other platforms. Yes.
Dr. Bose, so this feature was very interesting actually. I had to step out for 1 or 2 minutes, and I missed the detail about how are you able to do the simultaneous MFM and KFM measurement. Can you just briefly tell us from the cantilever signal perspective?
Sure.
How are you able to?
Sure. So the MFM measurement that we are making is still a dual pass technique actually.
Okay,
so we so we're still actually lifting the cantilever. But what we're able to do because of better lock-in amplifiers these days is to essentially minimize this time. So we are able to make more real-time measurements even with the lift technique that allows us almost real time to have both the potential and the magnetic and the topography data. But however, there is a lift involved in making the magnetic measurements.
So in that same lift so you do the KFM measurement in the lift?
No, the KFM is in single pass, but the magnetic measurement only is in double pass.
Okay.
Yes.
Okay. Got it.
Yeah. And because this is a polished surface. Because this is a polished surface, the magnetic lift may be only down to about 10-15 nanometers. You only need to lift up by 10-15 nanometers, maybe, to be able to get the magnetic signal. So yeah, essentially it's just faster measurements. Faster measurements by being able to sort of mathematically decouple multiple signals much faster than we are able to do 5 years back. That's really it.
Hello, sir. Excuse me.
Hi. Yes.
Hi, sir. I'm Pooja from NCL. I'm operating FM instrument. So I would like to ask that are you using this cantilever for same frequency for all three modes, means KFM, AFM, and the normal topography, or using
No, we are using at least two different frequencies in this case. The topography normally comes from the lowest eigen mode, maybe the fundamental harmonic, close to the fundamental harmonic. The potential, in our cases, there is, I don't know which instrument you're using and, when it was made, in a first generation instruments, the potential measurements, were typically made on a higher eigen mode, which the user had to really select, dependent upon certain calibration routines. You had to select whether you want.
Nanoscope 4A controller and multimode.
Nanoscope 4A controller. Okay. Yeah. So, typically, and some of it is down to software also, and not just the hardware. But, just to give you an idea, traditionally what you would do, and it's the same as, optimizing parameters, so you could look at it that way, is that traditionally, to make a Kelvin probe measurement, you locked on to a higher eigen mode, and you had to do some manual selections really, let's say, as to what you lock into, just to, keep it simple. In our case now, with current electronics, what you're able to do is that selection process itself is converted into electronics and software algorithms, so you no longer need to decide, which eigen mode will give you the best KFM resolution. The software and the electronics is able to do it for you automatically and in real time, I guess, if that answers your question.
Okay, thank you, sir.
Yeah, that, and as far as the magnetic measurement is concerned, it is probably going to be at a slightly offset frequency from the topography signal. That is typically the way people make MFM measurements. Just
Kilohertz,
off
yeah.
the harmonic. Yeah, just off the harmonic. Yeah.
Thank you, sir.
Sure. So yeah, I'm just going to carry on with the resiscope, and I have to be honest, part of the reason is that's because, we believe that this is, something that we have and, not a lot of people do. So, I'd like to talk quite a bit about this. And this is the resiscope is really something that, that has been offered for, I guess now for about 15 years on different platforms. This could be integrated, including into something like a multimode or, other AFM platforms. But since CSI started making our own AFMs, we have now integrated the resiscope module only into the CSI AFMs, But so I'd just like to sort of, introduce to you the kind of measurements that you can make. And why the resiscope is unique in terms of the ease with which you can measure a variety of different surfaces, which has a breadth of conductivities, starting from some and so you can measure surfaces across 10 orders of magnitude, in conductivity. So traditionally, to be able to do some of these things, you had to make physical changes, to the kind of preamplifiers you're using on your tip cone and things like that, So depending on what sort of conductive surface you want to measure, you had to pre-choose some attachments. With the resiscope, really, a lot of that is taken away and put into this, the black box here. And you don't need to make any hardware changes in terms of amplifiers and stuff to be able to measure a surface, that might have a wide range of conductivity across it, depending on how you've designed it, So you don't need to use different type of cantilever amplifiers, but all of that is nicely compressed into a digital box here, And let me talk you through some results, and that will give you an idea of what we can do. So the uniqueness of the resiscope really is in being able to measure, direct resistance and direct current of the surfaces. Classically, the AFMs typically measure only current. But with the resiscope, we can make independent direct measurements of both resistance and the current, and obviously make the corresponding, voltammograms as well. And yeah, this is an illustration of some of the data. That the technique itself, is very similar to, what's called the classical CAFM, or conductive atomic force microscopy.
So, one question actually: how are you able to go to resistance measurement as high as tera ohm? I wanted to understand that.
Sure, I'm going to come to that in a.
It's a big claim actually.
Yeah, sure. Yeah. So I'm going to come to that on the next slide. And, I think that to really be able to defend the claim will probably lead my colleague, But
I probably know the answer because.
Yeah, you probably know the answer. I don't. Yeah. But
because we do the in typical dielectric measurement.
Right.
We go to Novo control. We go to 100 tera ohm. So
right.
The isolation is actually, as yesterday professor from IIT Madras, he mentioned that you need a register of much higher value to isolate. Then only you can measure this.
Correct.
For example, you need probably 100 tera ohm or much higher resistance. Would you like to comment, Sabadiji, here on this value, 1 tera ohm? The technology behind that? Probably he's not.
As I said, Brashpodar, if some of these slides don't illustrate that, because even I'll have to look at the slide and let you know. But okay. We can definitely answer this question offline. Yeah. So, I mean, you've already sort of, revealed the cards in a certain sense, is that, the beauty of this technique lies in, measuring sort of, typical dielectric surfaces or, pattern dielectric surfaces, where you expect to have a significant difference between the resistivity or the current that you're drawing from one part of the sample to the next part of the sample, by nature of its design. And that is what the resiscope allows you to do, whereas previously you really were limited because, every amplifier had its own sort of, limitations in the range it could measure. this now allows us to do some of these more sophisticated measurements.
So can you do the AC measurement, AC resistance, like impedance stuff? Like,
yeah, I'm going to come to impedance also. You know, I have we have some slides on scanning impedance. So
it is actually another third feature which is new and interesting for me. This
sure.
resistance.
I will come to that, Dr. Podar. I have it next on my slides. So, it's fair to make a disclosure that, this is not really sort of, the design of some of these modules I had not involved with. And, so we'll probably have to take some of these questions offline if they get too sophisticated for me. But, I'm going to talk you through essentially how these measurements are made, and this is the point I was trying to highlight, for example, is that traditionally, unfortunately, you were only able to make conductive atomic force microscopy measurements at certain fixed values of gain, and you could not control the current, the localized current. So, then you have the risk of, when you have surfaces, you get suddenly high current, and a particular feature of your sample, and, that'll either sort of, burn out, your sample, or, you're going to run into other kind of problems, And the other disadvantage of traditional techniques, they're unable to sort of, isolate, some of these, local current responses, and that's what has led us to develop the RISCO. So as you can see here, and Professor Podar, if it's okay, we'll have an offline discussion on how we're able to make some of these measurements.
No, it's okay. Please go ahead. Yeah.
Thanks. Yeah. Okay. Yeah. So just to give you, I guess, so what we're able to do now is quite remarkable, I would say, and this is, if you look at the graph here, this is a calibration standard in a certain sense that we use. So you can clearly see, the range of resistances that we are able to measure, at least, this is just the calibration standard to calibrate the module. But you can see that, we can go from, 10 kiloamps down to, 50 ohms, 50 gigaohms, So, and that's why we call it. So I guess, again, the difference is that if you want to make measurements on surfaces of at this magnitude of difference in their, in their current response, traditionally it was not possible to do it, in one single scan, because you would need 2 or 3 different type of amplifier setups to be able to measure in particular ranges. The resiscope now allows us to combine all of that and make the measurement on the surface in a single scan itself. If that makes sense, Dr. Podar.
Yes, it's fine. Perfect. So I just wrote that it's all right not to reveal sensitive information without prior permission from the company.
No, it's not just sensitive information. I don't even, I don't know the design of it, to be honest.
Yeah, sometimes there are, companies.
No, we'll be happy to share it with you. It's just that I'm not the expert on it.
Okay, no problem.
Yeah. And so here is, I guess, once you have this, this sort of a capability where, you're able to, seamlessly move across, such a wide, range of conductivity, you're able to obviously, get over certain previous limitations on resolution. So things like, if you're patterning surfaces using local anodic oxidation, having the resiscope capability is going to allow you to sort of, envisage some more sophisticated patternings, I guess, on more sophisticated or, a wider range of surfaces, so as to speak, again, I'm not an expert on this, so I'm just making sort of, more generalized statements, but, that is fundamentally the option you will have now is to be able to, do a lot more, in a single scan rather than, what you would have to sort of, break down into multiple experiments previously, And you can change in my phone. So again, this is an interesting slide, because this kind of shows to you, some of the classical problems that you face, And if you look at the image on the left here, the conductive coating, that is on the cantilever tip, it's actually worn off, and precisely because of the problem, that I alluded to in the previous slide, is that, if you suddenly have a surface, where you suddenly get a very high amount of current, and you're not able to regulate that current, you're going to end up, burning your tip. The conductive coating is simply going to wear off, burn off, and that sort of thing. And that is obviously going to, not give you a good measurement, So that's the, beauty of, what we have developed with the resiscope, is it now allows you to make, some of these experiments a lot more cleanly, a lot more reliably, and, for a wide range of functional current properties of the surface. And this is one such illustration, I guess. You can see that this is actually graphene oxide again on a gold surface. And, we're trying to illustrate some of the classical differences, the difficulties in making the measurement. If you look at the image here, the bottom of it, it gets pretty dark because of, the problems that I just explained. It is difficult to get these stable conditions, on the graphene oxide isolates and then be able to measure their currents, precisely because of the same problems. And you can see the difference on the same sample with the resiscope, Once you use the resiscope, because, the resiscope is able to sort of, control the in a certain sense, really the amplifier, that's controlling the tip current. You come up with, really being able to measure the surface itself, rather than sort of, the tip having current issues and things like that, and, resulting in poor resolution. You're able to make, much cleaner and much improved current measurements on this graphene oxide layer. So is that a slide you like, Dr. Poddar? Or?
No, I am enjoying your entire talk.
Okay. Great. Yeah, but this is a nice slide, I think, that really shows
yes,
that
yes,
we can
yes,
have.
yes.
Yeah. And just to translate again, into another example here, and these are some other surfaces. I think again, what I would like to highlight is that the resiscope again also is a simultaneous measurement mode. So you can simultaneously measure topography, Kelvin probe, surface potential, and resiscope, all combined. If you if you do have that capability, and I'm just trying to go into some more examples, and these really try to highlight the breadth of applications that we have covered, in our laboratories and with our users. And these are some typical patterns, and as you can see, because you have such a wide range of measurement capability, I can pick up semiconductor features a lot easier, because I have this wide measurement capability, and the same translates into measuring organic solar cells. There's one example here on the right, and I'll come out to some of these challenges, because organic solar cells have their own challenges because the surfaces themselves are quite soft, and this is another critical point in AFM measurements, is that tips, typically can't, if tips end up damaging your surfaces, then obviously you can't make a reliable measurement, and with things like organic LEDs and organic solar cells, this is quite a critical factor, because, by nature, they're organic surfaces and they are, quite delicate. So, you cannot probe these surfaces, and in the process damage these surfaces itself, So we have to use some clever measurement techniques to be able to look at soft electronic surfaces, let's say, or organic electronics. And I'll come to these in the next 5-10 minutes, hopefully, But this is just a magnified images of, of what we were, of the last slide, really. And again, as the slide says here, the challenge with measuring organic layers is that you all often end up burning out some of these organic layers itself, in the process of making a measurement, simply because you do not have that control, that level of control over the current, in the tip sample interaction, and that ends up burning some of your surfaces, and that is typically the problem. And how we are able to circumvent that with the resiscope, is from this nice image on the right. And here's just some more illustrations. So if you want to make a like a dopant measurement, you can do that too, across the section of the sample surface. And this is a nice feature that we have on a nano observer, is that we can view the cantilever and the sample environment from the sides as well. And so it allows us to make some of these cross-sectional measurements on semiconductor samples a lot more easier. And
I love this result, this one on right hand side.
Yeah.
When this is wonderful way of showing in one image.
Yes.
I hope it is. It is one image itself. But
it's one image.
Yeah. Doping dependent change in the resistivity, marvelous. It's like
exactly.
It's better than any Star Wars movie or science fiction. Actually, it's right.
yeah. Especially, I think the fact that we are able to see the cantilever from the side. And the scan corresponds to the dopant profiling. Yeah, it's really a very nice image, because
I'm sure the resolution, like step size, which is the deeper detail. Maybe we can discuss later. But I will be interested in the least count and what is the in the resistance measurement.
Yeah.
How
I believe they're not very.
So
I think they're like maybe of a few hundred nanometers. Each of these dopant gradients here.
So are you able to match, for example, with some complementary technique, these resistance?
Sure. Yeah.
So that must have been done already, I'm sure.
Yeah, it's already been done. Yeah, we can share the results and we can have this discussion offline about.
So there is one student comment from student, one of the very bright student of my class. All of the students are very bright, but they are not asking questions. So one student has privately asked me questions. So she's asking, Nikitra, you can unmute yourself. I would love to you to ask the question yourself. Unmute yourself. And,
hello. Hello. Good afternoon, sir.
Hi.
Yeah, hello, sir. Yeah, actually, sorry to interpret in between, but actually, while going through your presentation, it's very useful. But a small doubt I have. The question is like vivid colors are there on the surfaces. What you have been shown. So what does it exactly represent? Any kind of property contained in the material or kind of resistivity property of the material? I don't know exactly.
Yeah, absolutely.
I couldn't understand.
Oh, okay, yeah. So
here we can see.
Yeah. So you see the color. Do you see the color coding scale here? So what this is essentially telling you is that the spots that are red, are at a higher, draw a higher current. Whereas this, wait a minute, is it the other way around? Because this is gold and is it okay? Yeah. So essentially,
you're doing fine because this is mega ohm. So reddish colors are higher in resistance, and bluish are low. I mean, more conducting surfaces are bluish, and insulating surfaces are reddish.
Reddish, yeah, correct. Yeah, exactly. Yeah, that's what I was trying to clarify, because the substrate is gold. So hence the darker regions are actually of higher conductivity, and the brighter regions are of higher resistance. If that clarifies what you were asking me.
Hello.
Yeah, is that clear now? Or?
Yeah, I cleared. Yeah, Thank you, sir.
Yeah, cool.
I have one question, please.
Please.
What is the lateral resolution for this image?
So I guess we can look into some of these spots here, and just from my experience, I would say that typically we can go down to about 5 nanometers. In 5 nanometers in a spot resolution with the resiscope.
Okay.
Yeah.
Fine.
Lateral resolution is limited by. It will be. It's not the machine problem.
Yes.
The fundamental problem of tip conversion, and
right.
So it will be with any microscope the same limit, I guess, right?
Right. Yeah. So maybe it's a good point to talk about this. Is that typically the tips these days, the sharpest tips that you can get, will be down to a couple of 3-4 nanometers. If I BH them down. So so obviously the resolution of the current or the resistance map will depend upon how sharp your tip is, and normally tips that are meant for these kind of measurements are the sharpest around. So we only sell tips that we know are less than 5 nanometers in tip sharpness.
So are these doped silicon or they are coated silicon?
Actually, now we have a technology that we can use direct diamond tips, So the entire tip is a diamond tip, and that's down to about a couple of nanometers. These are quite expensive tips, but really, they give very nice data, sir. So,
yeah, but nowadays you also have a super sharp.
Super sharp
yeah, the super sharp tips. Yeah, the super sharp tips are down to about 2-3 nanometers, and then there's an atomic layer current coating on it. But the problem, with the coatings is, as we have just discussed, is that these coatings can burn off, typically. So that is why you're better off with a whole diamond tip,
I have one more question, please. You have earlier said that the electrical signal they are weak than the mechanical one. Right. Then how you amplify them, and what about some stray signal if it is caught?
Okay, this is a question we can again discuss offline, maybe, because this comes down to how instrumentations work, So if you send me an email, I will try and do my best to explain this to you, But I mean, this is a fundamental instrumentation question, especially nano instrumentation. But yes, it's a very relevant question. I'll answer that for you, with some schematics. If you send me an email offline,
Fine.
Dr. Pota, this actually answers the question. So, there you see one of these resistance bands is about a 30 nanometers in section, So, I guess, that is the sort of resolution that we are able to go down to. Yeah. And here's just another example, this is a molybdenum disulfide surface again, on gold, and again we can look at some of these measurements, and we are able to characterize, the potential difference. And this is just to illustrate, various different.
I have one more request that going by the variety of questions from various backgrounds, because there are chemistry and biology students. So just explain the why, the current scale or topographic scale, the color coding actually, as Nikita asked this question.
Oh, okay. Yes, sure. Yeah, sure. So, So, I mean, this is obviously, fundamental to all AFM images. Basically, what the color code tries to do is to bring the third scale, that is the third leg scale. So you have X and Y. In topography, the Z in AFM images, in a 2D image, is color coded, So what that means is the brighter spots are at a higher height and the darker spots are at a lower height, So it's a third dimension, So if you plot this in 3D, these areas would be taller than the background, That's what it means. When you come down to the potential image, the reddish areas, the redder you get, means that this region, in this particular case on this MOS2, you have higher surface potential than compared to the background, that is the gold substrate, and that is what is represented on this graph here. You see the background, that is all the yellowish bits, they are at this potential, and the red bits are at the higher potential. That's essentially what we are trying to show with the color coding here. So the color coding, in a certain sense, is the intensity or any functional measurement basically of the surface. So X and Y, and the color represents the voltage response, or then translate into surface potential differences, and that sort of thing, depending on what image you're measuring.
So I would like to just put one comparative aspect. Can you go back, please, to the earlier? So all the students who are very familiar with the electron microscopy. So this is something very unique with the scanning probe microscopy, that you have another scale. Usually we have in microscopes we have two scales, X and Y. Quantitatively, we have no information in electron microscopy images most of the time in third leg Z region. So here we have so much of rich, you can see quantitative information and high resolution, the Z scale is actually much higher resolution actually, because it's largely unaffected with the from the tip convolution. Yeah. Okay, go ahead. Yeah.
Hello.
Yes.
Hello, sir. Sir, actually, small doubt I want to clear. This graph is there, surface potential versus number of layers. Sir, can you please explain this? I couldn't get it. This
sorry. Okay,
black dotted one and white dotted one, this right side.
Okay, so the left side one is topography. Okay, so it is just the topography of the surface. So what it is telling you is that you have the gold base here, right? All the dark regions, you can see that, right? And
yes.
you have the MOS2 flake here, right? This is the flake, right? Yeah.
Sorry, sir. No, so extremely sorry, sir. I'm not talking about topography. I'm talking about the one graph represented here, surface potential versus number of layers. Yes. So I want to understand this this graph actually. Above this.
Yeah, right.
This graph.
Okay. Yeah, so what it is trying to tell you is that, the surface potential decreases with increasing number of layers, So obviously you can see that, within this flake itself, there are regions that have a certain number of layers, and there are other regions that have a higher number or a lower number of layers, right? You can see that from the topography itself, right? So what the measurement is essentially demonstrating to us is that, the surface potential actually of MOS2 decreases as the number of layers go up, and I guess that's intuitive, right?
I would like to add one more thing. If you see this bottom right image, you see this dotted black line. So that is basically called section analysis. So so if you see this graph where you see 7 layer, 9 layer, that actually Kunal is trying to show that how you can differentiate between 7 layer and 9 layer, the subtle differences between surface potential. So you can see surface potential as well as work function difference when the number of layers of MOS2 on gold keep on increasing. So I'm really impressed with this result actually. Mind-boggling. Yeah, very nice.
Thank you. Yeah, that's perfectly. Actually, I missed the 7 and 9 layer. It was written there. Yeah, so what that's as I explained. What that's saying is that there's actually a potential difference. In regions where you have 7 layers and regions that you have 9 layers of the molecule. How are we doing for time actually? Because I think I'm going a bit slow maybe now. But if everybody is okay with it, I'll just go on at my current pace actually. And then,
we are fine. It depends upon. I'm enjoying this talk, so I'm not in a hurry. So depending upon you, actually.
Okay, fine. Yeah, I'll just go on till we finish.
How many slides you have? How many more slides?
Maybe another 10, 15 more. I'm going to try and speed up a bit, Professor Poddar, and we can take the questions later, and the more involved discussions, maybe we can take them offline.
See, I think all of this, some students are writing that they're enjoying your talk. So please go ahead. Yeah.
Okay, great, perfect. Okay, yeah. So this slide is now really an illustration of following on from the previous slide. So here we can actually, now that we know what is the difference in surface potential, between individual layers, we can actually map out this whole flake itself, and tell you where you have 1 layer, where you have 5 layers, where you have 7 layers, and where you have 8 layers, And we can color code, the flake, based on, the number of layers, really. And, that's a nice measurement, and obviously we're able to then go back and translate that into some numbers as well, So, I mean, this is really nice because this is almost close to the end game, I guess, Dr. Poddar, right? Because this is what you're trying to do, You're trying to establish the
absolutely impressive
distance coming from each layer. And this is a fantastic slide, actually, to be honest. And this is by the ICMM Madrid guys, and yeah, this is really, really nice to see.
I think students are loving your talk because you are going slower. That is that is very good actually. Yeah. So please spend more time on the images. That's a request, actually.
Yeah. No, absolutely. No, I mean, the only barrier is really my limited understanding of some of these images. That's all. I'll try and explain as much as I know.
It's a discussion, so I will also try to help as much as possible.
Sure. Yeah. And yeah, so again, this is a nice illustration, I guess, of when things can go wrong, and again, as I said, I'm not an expert on some of these designs, so I'll have to get back to you on how we circumvent some of these things, but you can clearly see what can go wrong. If you have some humidity, for example, in your scanning interface, you're going to end up with oxidation, and then you're not going to be able to make measurements and things like that. So these are really
almost 20 years back, I used to use this oxidative, humidity mediated oxidation of silicon surfaces as a writing mechanism. I think you're familiar with that. It's interesting way of writing patterns also.
Yeah, absolutely. Yeah, like local anionic oxidation, sort of, right? Yeah. So that's what I was trying to illustrate here, and I guess decreased. So, and these are just telling you, in a standard technique, in a standard AFM, you don't have really a lot of choices. You could only sort of try to reduce the interaction, the physical interaction, by reducing the force on the tip, or reducing or decreasing the bias, maybe to reduce the current. But this will only make the oxide smaller, and not prevent the oxidation. And that is the sort of the beauty of the AFM is, the ways in which, the radioscope, the ways in which we are able to circumvent, some of these classical problems of measuring, such a small interaction area where in ambient conditions. So they're exposed to all sort of contamination and, tip surface interaction effects. And this is really a technique, that follows on from the radioscope, and I'm not going to spend a lot of time on it. We call this a soft radioscope, and this really was developed because of the increasing needs of, organic electronics, because with organic electronics, often we're not able to make a classical radioscope measurement in the sense that, stay in contact with the surface all the time. But so what we developed is an intermittent radioscope technique, so it's quite, it's comparable to, the classical contact mode and tapping or non-contact mode of the AFM, where if you have soft surfaces with high surface energies where the tip tends to stick, we have to resort to not making a continuous contact to measure the current, but we have to make intermittent contacts, and as you can see in the inset image here, using the classical technique and using this intermittent contact technique, we are able to get much better electrical resolution, on the sample. And this is just, as I said, an extension of the radioscope technique, where, we're not making, a constant contact, but sort of, hovering over the surface and making intermittent contacts and making the measurements at those time steps. And obviously, what that allows us to do is get over, some of the classical tip sample interaction problems that we are likely to face, because of adhesion between the tip and the sample. As we know that organic surfaces are always a lot stickier, so the adhesion is higher. And in classic measurement techniques, this can lead to a lower resolution on the functional measurements, like current that we're trying to do here. So this is how the intermittent contact allows us to circumvent this problem. And I guess, here's another illustration of that, is that it's just about resolution. I said, you get much better resolution and a much more reliable way of making measurements on soft organic surfaces with the soft radioscope than what you would do with the standard radioscope technique, and that resolution really in terms of the current and resistance is illustrated in some of these profile graphs here. And okay, yeah, this is just another illustration of measurements with a soft radioscope on another semiconductor surface. The idea is that we have managed to sort of optimize these technique to a level where we are now able to make some very reliable measurements on a large breadth of surfaces on organic and semiconductor with a very high resolution of their functional property. And this is, I guess, you can do this obviously in temperature control as well. And this is one illustration where we can actually look at the change in behavior of this particular it's vanadium oxide as you change the temperature. So its resistance behavior actually changes with temperature, and we're able to capture that using the resiscope and constantly sort of ramping up the temperature of the sample. In this case, only a slight change between 25 to 50. So you can see that the whole resistance pattern on the surface itself changes. And I guess this is representing a scale of about 15 microns of the surface, So again, I'm not an expert on this, but, those of you who are in this research can really relate to, what this means. But this is the sort of measurement that we are able to make. And this is again a nice slide, I guess. This is again.
Can you go back, please?
Sure. Would you like to make some comments on this?
Yeah, because these materials are famous for metal to insulator transitions.
Right, yeah.
It's amazing to see some of these things. Vanadium oxide,
so,
VO2, vanadium pentoxide, these materials undergo, these sharp transitions in temperature. So that's what you are showing, actually, temperature dependent transitions. So that is interesting.
Right. Yeah. So this is like, classically the experiments where we could do on polymers where, these phase transition experiments, where we could observe the transition from glassy to crystalline transitions. Now we're able to do that in the resistance, on these sort of materials, as you say, that are quite sensitive to temperature in their resistance performance. And it's a pretty small order, actually, it's just between 25 to 50. So, yeah. And again, this is another polymer surface. The image on the left is classical of some sort of a polymer blend. And what we're trying to highlight here is that because we have this soft technique of the resiscope, we are able to bring out the resistance of this surface, with a resolution that you would struggle to with an ordinary conductive AFM technique, because of the nature of the surface, how soft it is, how sticky it is, and its underlying topography as well. And this represents a scan size of about 2.5 microns. So each of those grains here, you see, I guess, about 500 nanometers. So the resolution you're looking at, again, is down to about 510 nanometers. And again, another example. So this is a very nice example for this P3HT, is a very common organic solar cell material, as you know. And we're just trying to illustrate, the nice clean measurements that we're able to get on something like P3HT, So for those of you who are working on organic solar cells, we really think that we have the best solution in the market today, for making these measurements. Okay, the conclusion, I think. I wanted to show you some other slides. I'm just going to quickly go through my slides to see what else I have, So, Prespota, it looks like I don't have the slides on magnetic force microscopy in this slide deck, but I'm open to pulling up another presentation and showing you some of our MFM data, or we can now, close with the discussion on this for today. It's really up to you and the students to.
I think, Kunal, you're just telling that, we have this magnetic lateral force microscopy, MLFM, where you can apply the field, magnetic field in the inner axis up to 3000 Gauss, 0.3 Tesla.
Yes.
That was my
very unique offer from
complete you are in magnetic measurement. And Sir has answered my question already. That, you don't need to show, but that question is already answered, that how thorough you are in the magnetic measurements. But that it seems that you can change the field. And if you can vary the field, I'm not sure whether you can vary the field also.
We can vary the field as well. I'm just trying. We had some very nice measurements, actually. I'm just trying to get to that.
I have a couple of questions.
Of course. Please.
You have piezo capability, because it's very.
Of course.
You have it in this setup.
In fact, our ferroelectric measurements again are quite outstanding. I would say.
Okay.
And if you look at some of these, so this is this is one of our PFM, and these are all from customers in India, actually.
And you can
So
measure both
I guess it's
lateral
some
and
sort of
vertical both in PFM.
yeah, exactly. We can do both, and we can make these. What are these? Yeah, here's a 2D sample from IIT Mumbai. Actually, I think maybe I can't remember where some of these are. So yeah, we do quite a lot of PFM, and we measure these characteristics as well. This what are they called? This D. These are D parameters, right? This D11 and D for piezo's.
Yeah, I think Agilent was quite strong.
Yeah, we are quite. I think that maybe we need to have another presentation
no
on this because I even missed out on the.
Yeah,
but yeah, that's a nice image, of yeah. This is in fact, if you look at some of the probe manufacturers, they use our MFM image actually, and this is a spin-ice image, so we can really go down to some very nice resolutions, in magnetic domains. And once you have the external magnetic field, I can send you some of the animations where you can switch these domains, and these domains are not big at all. I can tell you, these are like maybe like 20-30 nanometer domains. And we can demonstrate to you that we can switch these domains, once we apply the magnetic field and reverse the polarity. So I can send those videos to you.
So impressive. I'm aware of the instrumentation part. So I won't be that much worried about the resolution in KFM because.
Sir, please look at this image. This image shows you exactly the switch.
See, nothing is changing on your screen, at least to me.
No, now it's changing. I think I'll put a video up for you.
No.
Oh, shit.
You have not shared that. You are still sharing the older screen.
Oh.
You have to change.
Well, we are not seeing any images.
Okay. So maybe, sir, okay, let me try to pull it up then. Wait. Let me try to get
because you are sharing the previous
I'm
slide.
still sharing the same screen, no? Yeah, sorry. Wait. Share screen. Okay.
See, but fundamental limits of MFM resolution, we all know that it is not because of instrument, it is because of magnetic coating and long range, magnetostatic forces being long range. So that puts the fundamental limit. That's we understand actually. So.
Yes, but let me just try to pull this up. This might give you a nice one actually. Share screen. Can you see it now?
Oh, you can see it, yes.
So as you can see, this is spin-ice lattice. So I think that, this particular domain is about 7 nanometers, So as we apply, as we switch the field, we can clearly see the transitions in the domains. And this is a facility with Shubhankar, by the way, in Nisar, Bhubaneswar. So.
Oh, Shubhankar has got this? Okay.
Yeah. To be honest, we are still working on getting the same resolution in his lab as we do in Paris. But yeah, we are able to make these measurements in his lab also.
Okay, good. We are good friends actually, Shubhankar and I.
Oh, okay. Perfect. So yeah, that's the sort of thing we can do. And I guess, Prasapudha, I mean, we can have another discussion on this maybe, beyond today's, because I think, we have a lot to offer, the microwave microscopy as well. And, if you wish, we can have another 20-minute presentation on just on microwave microscopy if you want, we can do it any other way. So.
Yeah, so thanks a lot, Kunal, for today's wonderful this seminar. And the way you explained all the basic concept from the beginning, that made your entire presentation really wonderful. I thoroughly enjoyed it. And also you allowed a lot of questions in between. That was like a classroom lecture. And that's actually best way to sell the instrument. If I were you, I will sell the same way to answer the questions. So I invite students to ask further questions to Kunal, if you have any. So please ask questions.
Can some in situ measurements be done in this instrument?
Yeah, sure. What sort of, can you be a bit more specific about in situ, like what sort of in situ experiments?
You have shown in the starting that some with humidity, some
Yes.
measurements you have done.
Yes.
So how is it possible?
Yeah, it's possible. I'm just, so one of the, I'm just trying to show you some examples, maybe.
Geeta, when you say in situ, we believe that you are talking about non-ambient conditions and simulating the non-ambient environments, like you can have a humidity, or you can have a temperature, or you can have a liquid, or you can have some gaseous atmosphere. So we have quite a few different options for making the in situ measurements and creating the environment around your sample. Or even, you, for example, we showed some the transition temperature changes, So you can do quite a few dynamic measurements as well. Like, for example, switching the magnetic domain, you can actively see how the, when you switch the field, how the domain changes and things like that. These are all part of the in situ measurements.
Sir, then what about the accuracy of
this, if you look at
these
your,
kind of
sorry.
Yeah, go ahead.
If you look at this measurement, for example, this is an in situ measurement in a certain sense, where you're trying to observe, the glass transition in this polymer. And, you're continuously scanning the surface over, I don't know, maybe like 20, 30 minutes. And by ramping the temperature, you can clearly see the transition in this polymer from its glassy state to its crystalline state, if that makes sense.
Yeah.
Can you see the video?
Yeah, I can see.
Yeah, so this is a typical example of an in situ measurement. Essentially, in situ measurements, the features that you're looking for in your instrumentation is, obviously in situ measurements are dynamic environments. And, hence the stability of the image, the stability of the image as you keep, yeah, exactly. Stability, I use the term stability loosely. The resolution, across, as you keep changing the experimental condition or the sample environment, the resolution that you can continue to have is what is critical, or what decides, what's a good instrument and what's bad instrument, I guess. And that's what we're trying to illustrate here, that I think we're going across a temperature range of about 100 degrees here. And you can see that, we're not really losing a lot of resolution, we get the same resolution whether we are at 30 degrees or whether we are at 130 degrees, and we're able to make some drift-free measurements. Obviously I'm showing you probably some of our best measurements, and there's a lot more to it than meets the eye in making some of these measurements. A lot of skills is involved. But yeah, to answer your question, yeah, there's a whole variety of in situ experiments that we can do, whether it comes to changing the magnetic field or changing the temperature or passing a fluid or passing a gas. It's all possible. Yeah.
Okay, thank you.
I have a question.
Yes,
sir, since we know that we have a lot of electrochemical sensing measurement techniques and all other techniques we have for sensing measurement, so why do we prefer this AFM over those techniques?
I mean, why do we prefer? Can you like name one or two techniques that you're trying to compare it to, maybe?
Like we have a lot of we have label-free techniques or labeling techniques for like biosensing measurements, or we have a lot of like optical measurement techniques and electrochemical techniques, CB measurement, IV measurement, and like this. So
yes.
Yeah, so if we compare all those techniques with AFM, so can we have more sensitivity, or can we have more? That is why do we prefer it?
Yeah, I understand your question. I think the way to look at it is this, I guess, is that the AFM, a sophisticated AFM should actually allow you to combine, all the techniques that you're referring to and give you, all the information in a certain sense that with the AFM, you're physically imaging the surface and you're also able to make the quantitative measurements at length scales, that you would get from as you're suggesting, some sort of spectroscopy techniques, let's say, that are essentially using chemical sensing. So the AFM is really sort of, I would say a complementary tool in a certain sense to some of these molecular-based techniques, spectroscopy-based techniques. But the uniqueness of the AFM is in the simplicity of using it. You just need to take a sample and put it under the cantilever, and you can start making a lot of these measurements. So I think you've got to look at the AFM as complementary to some of the other techniques you're mentioning. The ambition and the goal, of course, for us as AFM developers is to be able to give you the corresponding spectroscopic or quantitative information and measurements as you would get from an instrument that doesn't allow you to image, that's using a different probing technology, if that answers your question.
You can also do the label-free detection using our AFM. You don't need a label.
Right.
You can also do the electrochemical experiments by attaching the galvanostat or potentiostat. Actually, AFM is a very comprehensive equipment, and at the measurements at the nano level, sub-micron level and nano level, no equipment allows you to do this with such a simplicity. You don't need any sample preparation at all, like what Kunal was mentioning.
Yes, sir.
Yeah, that's a much more elegant way to put it. Yeah.
Yes, sir. I got my answer. Thank you.
Are there any more questions?
I think we can close this. Kunal has been talking almost for 2 hours.
Maybe we can have a separate, Pankaj sir, maybe we can have a small separate presentation only to smaller group about our magnetic lateral force microscopy and maybe a PFM. These are the 2 major things which we have not covered. We have a very extensive reports and imagings on that. If you wish, it could be a small.
We can have it actually. We can have it a separate talk, focus talk on some of those specialized things actually.
Yes.
But today also pretty much a lot of things are covered. But we can have a focus talk later on, smaller audience.
Sure.
Yeah.
Okay. I would like to thank you, Pankaj sir, for giving us this excellent opportunity.
So you call me please Pankaj, Kunal, you also, and Sabadi sir, you are senior people.
Sure.
Please call me Pankaj, I'll be happy. Kunal, you also should call me Pankaj.
Sure, Pankaj, no problem.
Yeah. So
thank you, sir. Thank you.
Yeah. Thank you very much. So have a nice weekend, all of you. And we thoroughly enjoyed today's talk. And thank you very much, Kunal, Dr. Kunal Bose, for giving us time, 2 hours of your really nice explanation. We appreciate, all of us appreciate, behalf of all my class students and other people who have joined in. I really, my gratitude to you for giving us time to explain the basics of AFM as well as your instrument, both actually. Thank you. Thank you very much.
Thank you.
Thanks a lot. Thank you. Okay. Have a good day, everybody. Bye.